Hi everyone. So today we're going to look at speed control in DC machines, and by the end of the session you should be able to describe the main methods of speed control and draw graphs of how the speed torque characteristic changes for each control strategy. So if you remember, we had an equation: omega is equal to EA on K phi. And EA, as you know, is Vt minus IA RA on K phi. We could represent that like this, as this equation here. Now if we look at this equation carefully, we'll see that it is essentially in the form of a straight line equation for omega and t, with omega being y, t being x. This value here is c, and negative, that is the slope. So we're looking at a straight line with a negative slope. So this is basically the and this is for a separately excited or shunt machine. So this is the basic characteristic, and we'll see that the thing that influences the speed torque characteristic are the armature resistance, the terminal voltage, and the flux. K, of course, is constant and it depends on the construction of the motor. So these are the three things that we could control to control the speed torque characteristic. So let's look at these in turn. But before we do that, we should say that you should, even though we're going to vary things like voltage and so on, you should never operate the motors beyond their rated values of voltage and current. Remember, the ratings have to do with the insulation systems. They have to do with how much heat the machine could dissipate, and if you go beyond that, you could damage the machine. So control could only be achieved by reducing these quantities, not by increasing them. You can't increase the voltage and current beyond their nameplate values. So first of all, we have armature resistance, and if we look at the equation here, we'll see that the armature resistance controls the slope. So the higher the resistance, the steeper the slope, the higher the magnitude of the gradient. So if we look at all of these, we'll see that here the y-intercept is not affected because we don't have r here there. It is just the slope. So if we look at a set of motors with different armature resistances, we will see that the starting torque is always the same, but we're going to get different slopes as we increase the resistance. So as we increase the resistance, the speed is going to drop off faster with increases in torque, and that of course is going to bring with it more losses because you have more resistance in the system. So that is one method. We should note here that we already talked about this, the no load speed being unchanged. If the resistance is increased till the point where the speed is 0, the motor is only supplying torque. That is, the motor is actually supplying a torque, but there's no speed associated with it. So this is known as holding, because it will hold the load at that position. And overall, this is a very inefficient method of control, because as we add resistance into the circuit, the amount of losses increase. So remember, the amount of torque depends on the amount of current. So if you have the same current but you have a greater resistance, you're going to get more losses. So it's not a very efficient method for control. The next one we want to look at is the armature voltage. So here, if we look at the equation again, we'll see that the slope this time is not changed. The thing that is affected is the y-intercept, which is this value here. Remember, we have y is equal to c minus mx, right? So this is your c, your y-intercept here. So if we reduce the value of v, then we should see the intercept changing to these points, but the slope remains the same, so all the characteristics are parallel to one another. Now, this is a highly efficient method because, of course, you're not increasing the losses in the system, so it's a very common method of control. But again, you could only reduce the speed. You can't increase the speed from the rated speed, because that would mean you'd have to go beyond the voltage ratings, which is what we don't want to do. And lastly, we have flux control. Now, if you remember the equation, omega is equal to Vt on k phi minus Ra on k phi by T, then we see that flux comes into play in both the y-intercept and the y-intercept and the gradient. So as k phi increases, as we increase the flux, then we're going to have the y-intercept dropping because these are on the denominator, and we're also going to have the gradient being reduced. So we see here we have the first one where phi is the highest, where phi is the lowest. We will have the highest starting torque, the highest starting speed, the no load speed, and then we would have the steepest gradient, and as we increase the flux, then we have the y-intercept going down, but we also have the gradient going down, so it becomes a gentler and gentler slope. Now, one of the interesting things about this is you could use this to actually go beyond your rated speed. So if this is your rated speed here, and remember we have EA is equal to K phi omega, we could, so omega is equal to EA on K phi, we could go beyond the rated speed by not increasing the voltage, but by decreasing the flux. So we call that flux weakening. So we have here now, and why we call it flux weakening is because, of course, TE is equal to K phi by IA. So if K phi drops, if it decreases, then we are going to have a decrease in the torque because we're going to have a smaller K phi here. So what happens is we sacrifice torque to get a higher speed without going beyond our ratings for EA and IA. So that is one of the interesting things for flux weakening that you can't achieve by using the other methods. And some points to note: no load speed is inversely proportional to the flux. The slope is inversely proportional to the square of the flux, and the speed is more sensitive to flux variations than variations in terminal voltage. So while you may have to change the terminal voltage a lot to get your changes in speed, you could use a little bit of flux change to achieve the same thing. So just to summarize again, you have to ensure that field voltage ratings are not exceeded, and make sure you do not exceed the ratings for the machine. One of the things you should also note is that we should not interrupt the field current, not the armature current, but the field current while the motor is running. And the reason for that, if you think about it, if you interrupt this, if the value goes down very low, then what is going to happen is you're going to end up with very high speeds, because remember omega is equal to EA on K phi. So if phi goes very low, the speed is going to shoot up. Not only that, since we have EA is equal to K phi by omega, if K phi goes down, then the EA is going to go down as well, and is going to lead to high motor currents. So remember we have, VT is equal to EA plus IA RA. So IA VT minus EA on RA is equal to IA, and if EA drops because you now have smaller phi, then the current is going to shoot up, and that can also damage your motor. So in summary, you should now be able to describe the main methods of speed control for the DC machines and draw graphs of how the speed torque characteristics change for each control strategy. And remember, here it's just the equation for a straight line. So if you can't remember it, you just derive the equation for the straight line and you look at what is the parameter. Does it correspond to the y-intercept? Does it correspond to the gradient? Or does it correspond to both?